Sebastian Peter. It's quite confusing which side I will move. Anyway, so Sebastian, I am Associate Professor in JNCSR. I am also founder and director of a spin-off, Brief Applied Sciences Private Limited, based in Bangalore. A bit about my research group. We do a lot of work in the area of solid-state and inorganic materials, particularly focused on developing exploratory synthesis of novel intermetallic chalcogenate oxide, etc., and try to understand their structural chemistry and link with the applications. We design the material for various applications like isothermal expansion, topological insulator, radiation detector material, spin glass behavior, dimensional reductions in air stable metals, etc. And last 3-4 years, we are concentrating on energy and environmental with a particular focus on fuel cell and carbon dioxide reduction that we started 2 years back. And we also work in water splitting, lithium battery, sodium battery. There are 2-3 papers coming up in this year on sodium-based battery. And we also work on biosensors, chemical sensors, a lot of organic catalysis reactions. So we develop the catalyst, we develop the material, scale them up, this whatever the commercial applications. I just go with the nanomaterial because this audience is actually, nano related, and I just want to give a tour and what are the different methods you can use for the synthesis of the nanomaterial. You know all this word, but still I just want to refresh your minds before going to my work. It can be synthesized either by top-down approach, take the bulk material, powderize and make it whatever the nanoparticles you are looking for. You can synthesize by atom and clustering and nanomaterial. So if you look at top-down approach, it can be done by lithography or bond milling. And if it is a bottom approach, it can be done by vapor-phase synthesis or liquid-phase synthesis. So you see that these are the various methods: pyrolysis, electrospray, spraying, physical vapor deposition, chemical vapor deposition, hydrothermal synthesis, salt synthesis. So we extensively use all this technique. Depends on what desired applications you are looking for. So we can control that. So if you look at colloidal synthesis, you look at that colloidal synthesis, it can form synthesis from the solutions and use the host material, organic ligands and coordination solvents, and use the whatever the metal you are going to imprint what you call the dopant at different time intervals, and you see that you will get a quantum dots, dopant quantum dots at the surface of whatever the base you are using. So basically, the product neither precipitates as a bulk or nor remains a solid. So the tricky part is actually how to control the temperature. You need a high temperature to have a better diffusion. At the low temperature, you need to have crystal growth formation. So you have to tune the temperature. You have to revisit several times the synthesis. And concentration of monomer is also crucial. How to control the synthesis. Chemical precipitation. We extensively use this one because we are working actually in the area of carbon dioxide reduction. Copper, zinc, and alumina. This is one of the commercial catalysts used in the industry, and they can control the nanoparticle distribution at the alumina surface. So here, what they are doing actually solution A, solution B, two metal. Either for example, if you are synthesizing this compound, cobalt nitrate or iron nitrate, and they mix it and add the precipitating agents, and then wash and post-treatment, and then you get the nanoparticle. So we just do the calculations, the uniform distribution of that one. And by controlling this ones, you can vary the stoichiometry or whatever the size you are going to synthesize. You know this technique well, hydrothermal and solvothermal. And you can see that you use a bomb, nothing but autoclave, and you start this reaction either in hydro condition or the organic conditions. You just form, there are two reactions happens here, hydrolysis followed by the dehydration, so you end up in the nanoparticle. So you can see that it can be, if you take this what you call the starting material of graphene, and you can use such a starting, say for example, if you want to titanium oxide, you can take the titanium source and then mix it and then heat it at a high temperature. It should be heated above the the boiling point of whatever the organic solvents or what we are using. So you have to again control depends on what process you are using. If you look at a plethora of compounds actually synthesized, you can see that what this is tin oxide holosphere, titanium oxide spheres is extensively used in the photocatalysis, and nanowire wires, nickel oxide flake wires, or tin dioxide. You can see that flower-like particles. So automatically, when it's a flower-like particle, you have more surface area. We have published one paper, and it actually give a better activity. Depends on the catalysis. It may not be always, but you can control the surface area. You can see that copper oxide architecture here. Here, again copper oxide to copper plus, the shuttling of copper plus on copper 1 can be controlled, and then especially carbon dioxide production. So Fe2O3, here it is using for, so actually medicinal applications and perovskite based systems. So a lot of, this is another method, self-assembly. Self-assembly extensively using organic systems, supramolecular, etc. But in metal-based system also they are using. So for example, it is a dispersion of whatever the nanoparticle, and then a self-assembly and evaporate it, and you can see that it's a uniform distribution of nanoparticles. Here, if you take two metal, either silver or gold, or silver, gold or gold, you can see that just themselves are assembled in such a way. And at the interface of the metal, the chemistry is completely different. It may form an alloy at the interface, and that changes actually automatically the electronic structure that is in favor of the activity or applications you are looking for. You can see that the gold nanoparticles and how beautifully that organized in this method. Electrode deposition. This is actually starting from the old generation Faraday's electrolysis principle. You apply actually a current. And what happens, there is a charge separation, charge transfer happens. The cathode, cation and anions, cation goes to cathode and anion goes to anode and deposit to the surface of the anode. And depends on how the potential or current applies that one. You will get, you can see that one, either this one or this one or this one. You see that's beautiful So automatically what happens, the surface area certainly, a huge surface area and more active sites actually available for the various applications. Chemical vapor deposition is another method. So here, through a chemical reaction. So the idea is actually you can use it either solid or liquid or gas or whatever, but it should be vaporized at a condition. And then it is actually deposited that whatever the non-active, what is non-liquid things actually it will accept gases, and then it can be gone, and the gases can also. And then the catalyst or whatever the material you can deposit in the surface of a split furnace. You can see that carbon nanoparticle, especially Y junction, one of the famous carbon nanoparticle actually reported, and still this can be synthesized by this method. Then physical vapor deposition. Here is actually combination of several activities. You can see that it can be vaporization of material from a solid source or transportation of vaporized material and nucleation both the surface and thin films. You see either it can be plasma sputtering or electron beam sputtering. So you see that a pulse laser beam, and then actually it's, there is a substrate and it is applying the energy and it's spraying actually, and then it is actually depositing. It's not spray actually, it's a plasma polymer, and then it is depositing at the target of whatever you are using for. So here PLD is another method here electron gun is using. Here is wet arc deposition. So we use this technique actually to get the uniform or surface of the nano. You can control the thickness of the nano layers by using this technique. Flame space pyrolysis. Here is actually this atomizers and heats. You can see that just a flame will produce a primary spray, and slowly it's depositing and the nanoparticle is forming. It's a kind of spraying actually, like how we use the paint in this case. Electrospraying actually is a mixture of solutions that contain selected material, and then we just press it, and then at the tip actually you can heat it and then apply the pressure and at the high voltage, and then result in the production of charged droplets. The big advantage is actually you can get the uniform size of the nanoparticle. It's a well uniform effect of nanoparticle. And and it will form within a short span of time. You don't have to wait for many days actually to get the like hydrothermal. You have to wait maybe 2 days, 3 days to get the nanoparticle. Lithography. Lithography is a kind of patterning. Whatever the size and shape and morphology, you can do. So there are different types. Either use photo sources or electron beam or X-ray lithography or ion beam lithography, depends on the source actually. You just ionize it and then get the deposition of that. High energy ball milling. So you synthesize the bulk material, use the mechanical force, and then by using the mechanical force you can itself top to bottom approach, and then you can actually make it as a nanoparticle. The advantage is actually, again, there is no chemical reagents involved in that one, but the disadvantage is actually you cannot have the perfect morphology. It's actually you are getting excellent non-morphological synthesis. Yeah. So these are the various techniques. Those who are working in nano field, they extensively used all this one. But there are advantages and disadvantages. Depends on what actually you are going to select that. So I just want to emphasize one point here, the interest of the chemist. Here you see that one you can control the morphology. Say for example, if you are taking a silver nanoparticle has either 111 crystallographic plane or 100 crystallographic plane or 110 crystallographic plane. If you are smart enough, you can synthesize what crystallographic planes depends on what applications you are looking for. Say for example, you are applying the surfactant. So this is the crystallographic plane 111, and that is favoring actually the growth along this direction and all this direction. These are all silver nanoparticles. So how many different morphology you can synthesize either this one or this one or this one or flower or this thing. So it depends on how you change the morphology, and each morphology plays a crucial role in changing that. So these are the various surfactants used in this one, starting from Zeta, BVT, PP, and so on. So, and this one follows a different chemical reaction towards that particular morphology. Here again, and then morphology or different morphology in different band gap, particularly photocatalysis, either it's a nano rod, nano shelf, or nano cages. You see that one, this band gaps will be changed upon this different morphology. Okay, so I just stop here nanoparticle synthesis. I just go to my work and what we have done with this one. There are a lot of applications, as I said, and this particular talk I talk about energy, environment, and a bit about biological applications, particularly the detections of drugs. And I don't want to focus on this one. Praveen gave a fantastic talk in this area, and I cannot match up with that biology part. I'll just focus on energy. So there are a lot of applications in energy. As you heard that battery or the fuel cell or supercapacitor, and then storage of storage devices or etc. So this is a nice article actually covered in this one. I don't have this is not clear. So you can see that this nanomaterial synthesis and then various way you can tune this this application, the wind on the fossil fuel, hydrogen, electricity, etc. And the environmental applications also, I just skip this thing. So the first one, the design of intermetallic nanoparticle for efficient conversion of CO2 to methanol. As you know that CO2 is one of the issue at the moment. It is actually causing a lot of global warming and other issues, and then we are in actually specific interest how to control this one and use an efficient source of the fuel. So we already initiated this project 15 years back, and then we are quite successful in developing the catalyst in this area. I just want to highlight one work recently published in Nano Letters, where it is copper nanocrystals. Copper is the most used catalyst for the CO2 methanol. So different way, it can be synthesized in nanoparticle, it can be used in a surface, in oxide form, in intermetallic forms, and in wherever. So here what they have done, copper nanocrystal encapsulated in zirconium based metal organics framework. And then by using this way, they could able to improve the efficiency of this material. And you can see that they used hydrogen, no carbon monoxide required. So usually in the industry, carbon monoxide and hydrogen syn gas, they treated and then formed the methanol. So here in this case that is not required. And then what they have done, they used various metal organic framework, zirconium based framework, they represented as UIO 66, this model, you can see that one. And this is the metal organic framework. And you see that the copper nanoparticle actually encapsulated at the cage of, from inside the cage of the metal organic framework. By doing so, it's a kind of a site isolation of nanoparticular active sites. So the reactants, that is nothing but carbon dioxide and hydrogen, would able to actually reach at the reactant, at the active sites very efficiently, instead of you have an agglomeration model. So you just actually, instead of having an agglomerated particle, it will depend. So by doing so, they could able to reach 100% selectivity towards methanol. There are a lot of mechanistic aspects actually discussed in this paper. I am not going to do it. So we have used this kind of concept in collaboration with the Professor Mesh Walkmer and team in NCSR. What and how we do actually, we selected the plethora of compounds that reported based on the logic and science behind, and we requested the Professor Walkmer to use the mechanistic pathway starting from hydrogen splitting or the different step of hydrogen, carbon dioxide to methanol formation. He takes each elementary steps of this reaction and doing the catalyst, first principle DFT calculation and machine learning program using CatMap, and then he arrived at a conclusion that, so you have the catalyst, out of this 50 catalysts, you have the catalyst, this is called this volcano triangle, and the triangle where at which the middle actually giving the best catalyst. You can see that one is actually carbon at first and this is oxygen at first. C double bond or double bond of oxygen cannot be absorbed and carbon can be absorbed. The energy will be calculated, and based on that one, he will just give the catalyst which one is good. And we synthesize the catalyst. This is one example we have synthesized. Intermetallic on SBF15. SBF15 is nothing but as a mesoporous material. We synthesize, but this is a well-known synthesis strategy. We have synthesized. You can see that so we will get beautiful morphology of that one. And followed by incipient wetness impregnation, where at which actually the metal salt actually impregnating and doing the reactions at the surface or inside this thermoporous material. And the steps you can see that evaporation, calcination, and followed by the reduction with the hydrogen at 800 degrees C for 5 hours. The catalyst either at the surface of the mesoporous or at the inside of that one. So how do we do that one? We just characterize. You can see that we characterize this is a mesoporous, and you can see that this is actually exactly matching with the absorption isotherm. Whatever. And you see that one is mesoporous SPF15, and this nanoparticles actually at SPF15. We cannot say that it's completely inside or outside. But we understand surface area difference, and based on that one, some of them are inside and outside. And we characterize by XRD, and you can see that there is a limit, saturation limit. You can encapsulate only maximum 23% of this nanoparticle can go inside. And I will come back to this XRD figure later. And we have done a series of different compounds, copper 7 indium 3, nickel 2 indium 3. Keep in mind, copper is good for CO2 conversion, and indium is actually selective for CO2 methanol. So that is our main idea we have used. And we have done a series of calculations in the band center, energy deposition, where is highest occupied and lowest occupied, and how this absorption, what are the mechanisms going through, etc. And a series of chemistry, we have done that one. And then we have done this reaction, and we have scaled up. You can see that it can be synthesized in the small scale, even up to kilogram scale we can synthesize, because we are developing this, the technology in the larger scale. So you could do the process calcining and put it in the binder and then reduce that one. You can synthesize in this kilogram and process in a various formats. For the catalyst industry, if you want to do it a thermochemical, this is a thermochemical reaction, so you have to develop in the large form extruder. So we have done this reaction at 250 degrees C at 50 bar pressure, and then there is conditions, the ratio of hydrogen to carbon dioxide using nitrogen as internal standard, and we have calculated the conversion and selectivity, And this is our reactor. And I just want to emphasize one point actually, there is a thermodynamic limit of CO2 to methanol, there is nothing but 25 degrees. The idea is actually push the thermodynamic limit with the appropriate design of the catalyst and this reactor. So we have designed the reactor by using the knowledge of the chemical engineering and various reaction steps involved. And we got the conversions, 45% of conversion with the selectivity towards methanol 90%. So this is by far much better than the best non-copper zinc aluminum catalyst. So we have developed 5 kilogram of CO2 in a day, and this is 2 hours of reactions. You are getting methanol, 90% purity methanol you are getting, and no, I did not mention that point. Carbon dioxide we are capturing from the flow stream that is coming from the power generation sector. Coal or natural gas power generation sector, we can really collect and capture 90% of that one with a 99.95% purity. Okay, but at the moment the NCSR we are not doing, but we have different locations to work on. Exactly.
But the rate of methanol that is stored methanol you are running up.
That's a 2 hours stored methanol. Yeah.
So how much methanol?
So it's a one cycle. It is actually 45%. So 5 kilogram it is calculate approximately half a liter of around that. Yeah. So we have started based on this technology. We are scaling up this technology towards the 400 kilogram. It's already, each is in the process. It's going to be established and commissioned by April in the NCSR. And there is a 2-ton plant in US actually we are constructing one. So we are scaling up this technology to the different level. And this is I just want to advertise myself. We are in the global competitions called NRG COSIAC Carbon X Prize. This is a $20 million competition. Out of 147 team, we entered into the final round. Now reduced to 10 teams. We are the only Asian teams, I would say, in the final round of that one. And we got, we were selected as one of the best startup by Karnataka state government last year, previous year. And ONGC also selected as one of the best startup from a pool of 2,700 plus applications. So we have a lot of, these guys are actually doing the carbon capture, carbon-based solution. And they designed the reactor, and this is the competition. Shell is already, evaluating the technology. It's a globally, they're a team of 6 members from United States. They're, testing this technology. So, a lot of chemistry there. It's a very complex chemistry. CO2, conversions, you can get them in 17 different products. It depends on how you design the catalyst. And you can see, starting from carbon monoxide, dimethyl ether, even urea, or even cement, you can produce that one. It's very complex, and it's a lot of scientific challenges involved in that one. So another project I want to talk about electrochemical dealloying of nanoparticle to achieve platinum-like activity for hydrogen evolution reaction. So here we have synthesized palladium copper 3. The idea is actually non-platinum based copper. And we alloy them, and we can make them either in the sphere or in the square model. And if you, as I said earlier, the major crystallographic plane is actually exposed here. One is 1111. So here is 100. And so anyway, we have done this one. How to understand that? We have to go to this fundamental chemistry and then in detail. And if you have this plane corresponds to 110 and 100, so you just say that when it is an ordered structure. You can go in a bit more detail into the structure. Palladium metal has a position only for A, and you add copper, it can go to its own position, or it can find itself in different positions. So you say, for example, if it's a disorder, it will go its position. If it's an ordered, palladium find a position 0, 0, 0, and the copper will be in this position. So we can actually see that one, which position and detailed crystallography studies, exapts, and then other studies we can do. So you see that this model. So here, palladium has its own position, and then copper has its own position. Anyway, we have done electrochemical studies, and basic electrochemical studies, hydrogen evolution studies we have done. You can see the potential, onset potential, 2 forward. I hope you know that one, what is the power potential. And it is not great value. It is better to close to 0. That's actually platinum dust. It's close to 0.1. That is platinum dust. So what we have done, You can see the potential range we have chosen. This is the potential range. And when we actually change the potential range, you see that there is a copper oxide formation and copper oxide reduction peaks are coming out. And this is actually nothing but copper is actually slowly etching out from the system. We continue this one. This copper oxide formation peak slowly going down. The copper needs steps actually coming off. And same as here, copper oxide reduction peak also goes. So that means actually from the palladium copper system, copper is slowly etching out. It is actually generating as a palladium copper 3 minus X system. So schematically we can represent that this is a coordination environment. One atom is going, another atom is going, another atom is going, and then reaches a stage at which there is no further possibility. So we have tested this one each cycle. I am selecting only 100 cycles, 100, 200, up to 2000 cycles. It was the onset potential was here. As we remove the copper, this slowly move towards the better onset potential that is close to platinum. You can see that compared to platinum. Commercial platinum we purchased from the market with a 48%. You can see that the onset potential, and our catalyst actually is showing close to platinum. It's a kind of a platinum-like activity. And it can be explained by the kinetics and then what mechanistic pathways are following. So there's a famous Stuffel's law. It's nothing but B value, we are getting 34 for our catalyst, and then platinum is actually 29. It's close to platinum. And exactly, this is another charge transfer kinetics, and you can see that one, this Fermi circle, whatever the lowest, actually less charge transfer, and that gives actually the better activity in our case. So how it happens? So we actually got the support from Professor Sebastaian and group, and then they have calculated. They have taken this coordination environment and did the calculation delta G. Delta G is nothing but it is actually follow the Sebastaian principle. How the optima absorption is favoring the best activity. And so ultimately is actually delta G is close to zeros for the better activity. That's what the platinum is actually doing. Remove this one, and if you see that N is equal to 9, nothing but all this copper environment is there, atom is there. And if you remove one atom, it's dropping down, another atom is going down, another atom going down, N5 is equal to 0. After a particular, one more atom, it's actually below platinum. So what it does actually, exactly if you look at that one, here is, it reaches a point and going back in 1000 cycles. So exactly, whatever short that one. So the density of state also, there is a shift in the energy level also showing that this is supporting that. And we have done in a D-alloyed nanoparticle, it is not changing. There is always a confusion that when copper is actually etching, it actually loses its actually the original structure. It's not happened. We have done the characterization based on that. And then we have done this detailed analysis of when D-alloyed and asynthesis, and we have also, XRD, I'm not showing here. Okay, so that is second project. And third one, design development of non-platinum based materials as efficient electrodes in fuel cell. We extensively work on fuel cell for the development of non-platinum electrodes, both anodes and cathodes. And those who are not familiar, this is fuel cell. You can see that anode at which the oxidation reactions happen, and when the oxidation happens, ions are exchanged through the proton exchange membrane and the electron external circuit, and the reduction is happening at the cathode. So there are two problems here. One is actually how efficient the oxidation can happen, that actually dictates the efficiency. Second problem is actually cathode. This reaction is sluggish in nature because whatever the intermediate that forms strongly acts on the surface of the platinum, and that actually kills the kinetics very badly. So platinum is the king of this both reactions. So why it is so? Because it is most efficient catalyst for the oxidation of any organic molecule. Basically, we use ethanol or methanol or formic acid or methane, etc. for this reaction. And platinum does not oxidize even in air at high temperature and not affected by common acids. Mostly this reaction done in acidic media or alkaline media, platinum is very stable. And third is high work function. And ability to catalyze the reduction of oxygen, good resistance, high exchange current density, etc. But the problem is that it's expensive and it's not abundant in nature. And it's very small amount available actually in our crust, and they're easily poisoned by carbon monoxide, sulfur, or halide, or other reaction intermediates. So these all problems are there, and then we have done a lot of strategies The strategy is number one, non-platinum, and alloy with the second metal. So when you alloy, you are changing the electronic structure. You are changing the D pair. So automatically you are changing the delta G and other parameters into the system. And ordered compound. Ordered compound is nothing but, you are arranging the active species in the vicinity of inactive species. You don't need any supporting material. The deficiency you can tune the deficiency, it depends on how you are strategically good in actually designing. And that also changes the structure, what you call the electronic structure. And you can control the sizes and morphology. As I said, the crystallographic planes you can control efficiently. And then in situ, support and design support uniform distribution and ligand effect and de-alloying, atomic scale engineering, atom scale. Even you can pick an atom and then how that can be changed in the structure. So I am not going into the detail. I will just go show a couple of examples here. So why nanoparticle? Nanoparticle is nothing but it's actually the amount of the catalyst can be reduced. There are a lot of the international projects is actually happening actually how to reduce the catalyst and keeping the activity better and then improve the overall this one. The lowering of our potential losses. So this catalyst also can be our potential can be reduced, and then when the size of this nanoparticle reduced, most activity at the edges and corners of the atoms. So when you are precisely tuned, you have more edges and more corners and more active species. So only it is applicable to 10 below 10 nanometers. And we use an ordered nanostructure. This is one commercial catalyst, platinum ruthenium, which can be available in the market. So as I said, platinum is actually showing sluggish reaction kinetics. So they actually alloyed with the ruthenium. What ruthenium did actually, this strongly absorbed oxygen containing species, and then whatever carbon monoxide absorbed at the surface of the platinum react with the hydroxyl, and then it is cleaning the surface. So that is the trick. So ruthenium is acting as a scavenger here. So similar strategy we have used, but keep in mind ruthenium is damn expensive. Morphology, you can see that platinum has three planes, 111, 100, 110, and you see that there are a lot of calculations. This is Jack's paper, and they calculated different plane 331 or 310, 311, and they can synthesize this model. If it is a rhomic dodecahedron, this model. If it is a tetrahedron 331, you can synthesize all these catalysts. It is not difficult, it is all well established. But when you synthesize a compound, an alloy or intermetallic, the synthesis may not be that easy. So here you see that octahedron 111 is more active. Is that 110 is more active than 100, more active than 111. So we have used this concept very efficiently, and a couple of patents also in this direction. I am not showing that. Here, how we can control deficiency. Here, for example, palladium to Ge for ethanol oxidation. This is the crystal structure. This is a hexagonal system with a P6 bar 2M. You can control this, germanium deficiency in such a manner. You can eliminate. You can knock out of one germanium if you control the synthesis. And that's very clearly visible in XRD pattern. In our XRS data also very clearly showing that one germanium is out of the picture. And you can feel that germanium with the third metal. Say for example, we have one paper under reviewing chemistry of materials that manganese is substituted and nickel is substituted. That is improving the activity further. And you can see that well separate nanoparticle and agglomerated nanoparticle depends on how you do the synthesis. Anyway, we have done the ethanol oxidation. What do you find that actually, this is actually in terms of activity it is better than palladium on carbon commercial catalyst, and the stability also pretty good in nature. And we have done actually stability and kinetic behavior, and you see that when this this is called chronoamperometry, where at which you can see that for 1000 seconds our catalyst palladium to Ge36 is nothing but 36 means that 36 hours of reaction, and 36 hours of reaction this is completely filled, and if it is 24 hours reaction around 12% of germanium is deficient. So you can control it by varying the reaction condition. And the kinetics, you can see that this is a tuple equations one. From there we can calculate the number of electrons transferred in the reaction. If the total number of involved in this reaction is 12, if it is actually number of electrons is 6, actually it is following the 2 steps reaction. It is a 2 and 3 steps reaction. So if you understand the mechanism of ethanol to oxidations, it can follow multiple reactions. So we have done oxygen reduction reaction also, where at which it can follow the path, oxygen with the 4 electron, 4 proton, and then it will directly convert it to H2O. It can also follow through this multiple reaction pathways. It first will follow this, this pathway where at which the hydrogen peroxide, and then in the second step this one water. But for oxygen reduction reaction, we don't want multiple pathways because it will reduce the efficiency. So we want to have a single 4 electron pathway. So because of this nature, this is a sluggish nature. So there are a lot of enormous amount of work actually in intermediates particularly. There is a paper in 2009 published. This is again called a volcano plot, where at which the potential differences versus the logarithm, current density. You can see that platinum stands here. So platinum is actually 0, and the current density is close to this one. But they discovered this compound platinum 3Y with better current density, efficiency. So we have used this one compound. We actually discovered palladium copper 3, where at which we control the morphology, and our stands actually somewhere close to that one. This is not published, but the patent is on already there. I don't want to go there, but I just want to highlight. What I mentioned, that this stability of the catalyst is not really great. And we have done one work and that published in JMCA and followed by another paper just accepted in ACS energy letter. So here what we are synthesizing is palladium 70 Sc15, and we did all this characterization. My student took almost 1.5 years to get the pure compound. So it was extremely difficult. 1.5 years exactly he took it. And what he did actually, he did this activity. I am not going to other reactions. 50k cycles, 50,000 cycles. Usually the catalyst is stable in the range of 5,000 cycles. So it is actually almost 2 weeks actually continuous running. Student has to sleep in the lab to do this experiment. Every 3 hours oxygen you have to sparse the oxygen. So he has done that one, and you can see that one, this intact. There is no onset potential or the current actually change even after 50,000 of reaction. So he has done a lot of analysis. You can see that there is a selenium oxide peak is forming and selenium reduction peak is forming. And even after 50,000 cycle, this is actually in each steps. Every 10k cycles, and you see that there is no difference. And we have done a detailed in situ excerpt studies to understand what is the mechanism. And each 10,000 cycle, we have taken the solutions and did the ICP, and then we understood that ICP is actually the amount of selenium slowly building up. That means actually selenium is coming off from the system, and there we proposed based on the complete studies, the selenium is slowly etching out of the system and protecting the surface, and then keep the activity of palladium as good as from the first cycle. So final analysis, we have done XRD, and then we got XRD peak as a palladium peak. So it's a kind of a different way of synthesizing palladium. Now I am going to biology. So we have developed some platinum based system. So here platinum on cerium oxide and copper oxide carbon based electrode, and this is actually electrochemical detection of dopamine and paracetamol. So this is actually, I accidentally ended into this field. So we have developed this catalyst basically for fuel cell, and how we synthesize the catalyst, we use copper oxide as a sacrificing agent. Copper oxide is not a conducting material. So you can see that when you can synthesize 200 nanometer box down to 50 nanometer. Below 50 nanometer we cannot get it, it will form as a powder. So we synthesize, and we replace actually copper with the cerium dioxide. And while doing that, copper will etch out from the center, and it will form actually nanoboxes. Okay, so when it forms nanoboxes, platinum actually reduced at the surface of the nanoboxes, and platinum reduces the platinum metal at the corners and the edges mostly, and at the faces as well. And we have taken actually TM image from each step, starting from this step to this step. And then you can see that there is a changes of the shape. It's not shape actually, the surface is actually changed, and then it's just characterized by all the element at the surface of this one. This is also characterized by XRD and XSAPs and XPS, by various techniques, and we confirm that one platinum is actually uniformly, reduced at the surface of the nanoboxes. So we can control the concentration of the platinum also depends on whatever the input we are giving. We have used the electrochemical sensor for the paracetamol of dopamine, and you can see that this is a differential pulse voltammetry, and within this potential range and various concentration of dopamine, and this is a paracetamol. You can see that 160 micromolar of this one, and down to 0.5. You would be able to detect actually even the smaller concentration of 0.0979 micromolar of detection for the paracetamol and 0.091 for this dopamine. So we have efficiently found that one, and then what we have done, we just mixed both. And then, for example, if you have in a paracetamol dopamine also in the same level, you can see that one. And anyway, we have detected both at this concentration 0.5 down to 0.5 micromolar concentration. And what we have done actually, we have collected this human serum and urine to test that, feed that and test that. When we found these concentrations, you can see that very good concentrations in the detection limit, down the detection limit by using this technique. So when I just submitted the paper, I did not understand exactly how to sell that because I am not a biologist, I was a chemist. And the moment I published the paper, I got a call from the Hindu, and it was highlighted in the Hindu as a special article in one of the science magazine. And finally, so calorimetric detection of copper 2+. So here it's really nice work. So it's assisted by single crystal growth mediated transformation. So we have discovered two new complexes. One is a dispersing complexes. I'm not going into the detail. This is a organic molecule, and then the dysprosium metal is actually here, and this is neodymium, and we have done extensive crystallography and found the crystal structure of this molecule. Both molecules, these are the complexes. And we have characterized by using various IR and Raman and etc. and all. What we have done actually, we tried to use actually a sensor, and first we dipped the crystal, selected crystals in this copper solution, copper CO2+, and we have captured this images at various intervals, and you can see that color from gray color to change to bluish color. So there is a structural transformations happening in this one. And even actually we selected different solutions: cobalt, nickel, zinc, cadmium, silver, gold. Each one we have tested. But in those solutions, other solutions, actually there is no color change happen. But when you mix with all the solutions, and you can see that when it's selectively capturing or sensing copper, and then how we can identify. Anyway, so we compare this one, how much molar concentration, whatever the selectivity, comparing with the known systems in here. How we can understand is the copper is actually selectively sensing. So we have tested, and we have collected some single crystals from here. You can see that one, and this is actually basically that is a single crystal. And one needle we have taken, and then took the single crystal XRD and refined the structure. And then we see that the structure from here to here, actually basically it is changing from orthorhombic to tetragonal structure upon copper is actually capturing the system. So there is a single crystal phase transition happen. So the idea for the whole game, so we designed the nanomaterial by various methods, and then just we try to understand this nanomaterial. So particular focus is actually energy and environment. We use it as efficient material for the desired applications. With all this one, I would like to conclude with an acknowledgement to my group. This is my research group, Professor C.N.R. Rao. So he is supported from the beginning for the various facilities and then various support. Professor Umesh Vakmare, he is involved in a lot of calculations and various funding. And thank you very much for your kind attention.